Welcome to The Explainer. Today, we are diving deep into the mechanics of preemptive SLO error budget burn alerts, which is really just a fancy way of saying how to keep your systems highly reliable without losing your mind. We're pulling this incredibly useful framework straight from Chapter 12 of Observability Engineering. Look, if you've ever dealt with threshold-based alert fatigue, getting jolted awake at 3 a.m. because of a random CPU spike that didn't actually affect a single user, then you know there has got to be a better way. Well, there absolutely is. It's all about service-level objectives, or SLOs, and more importantly, how we can monitor them without completely burning out our engineering teams. Let's get into it. We've got a really packed agenda today. First, we'll cover managing your error budget, then forecasting budget exhaustion, followed by short-term versus context-aware alerts, time series versus event data, and finally, acting on those burn alerts. All right, let's jump right into Section 1, Managing Your Error Budget. To really grasp how we can build better, actually actionable alerts, we have to start with the core concept that makes this whole framework possible. An error budget is exactly what it sounds like. It's the maximum amount of system unavailability that your business is willing to tolerate. Think of it literally like a bank account for your system's reliability. We want proactive alerts when our spending rate spikes way too fast, right? We don't just want to notice when the account is completely overdrawn and bounced. If your SLO target is to ensure 99.9% of requests are successful, your error budget is that tiny remaining 0.1%. That is your strict allowance for failure. And these error budgets are just absolutely crucial because they align your engineering and product teams. They provide a shared objective metric. It finally puts an end to that classic tug-of-war between wanting to ship new features super fast and needing to keep the system perfectly stable. Just imagine a standard 3-week period where system errors are constantly, quietly chipping away at that acceptable budget. Eventually, you're going to breach your reliability target. And trust me, you do not want to find out about a problem only when that remaining budget hits absolute zero. By that point, you've already violated your agreement with your users. Customer trust is taking a hit, and your engineering team is definitely scrambling in a total reactive panic. The entire goal of an effective alerting system is to catch that downward trajectory early enough to actually do something about it. Which brings us to a massive operational challenge. How do we actually calculate our trajectory so we know our system is failing before the users do, and certainly before that budget completely runs dry? If we can just foresee the emptying of our error budget, we get this golden opportunity to step in, push a fix, and prevent the breach entirely. But how exactly do we mathematically see into the future? That brings us to Section 2, Forecasting Budget Exhaustion. So the real secret sauce of preemptive alerting is forecasting. What we do is take our current failure rate from a recent baseline window, think of that like looking in the rearview mirror, and project it forward into a look-ahead window to predict exactly when a breach is going to happen. Effective burn alerts must forecast the amount of error budget your system will have burned at some future point in time. So we take a trailing baseline, say the last hour or maybe the last day, calculate the exact rate of failure, and mathematically extrapolate that into a forward look-ahead window. This right here is exactly how we escape those totally meaningless CPU alerts and start triggering alerts based on actual impending user pain. Let's put some actual numbers to this to make it concrete. Imagine a scenario where your service handles exactly 43,800 units a month. With a 99% SLO, your absolute error budget is firmly capped at 438 allowable failures. Boom. That gives us a concrete, non-negotiable number to work with. Now let's say in the last 6 hours, you've suddenly seen 25 failures out of just 50 units processed. Your proportional failure rate just spiked to 50%. If we do the math on that trend continuing, you won't just experience a slight degradation. No, you're going to burn through hundreds of units in a matter of hours, completely blowing past your 438 failure limit long before the month is even close to over. You need an alert right now. Let's move on to Section 3, Short-Term versus Context-Aware. Now, how do we actually run the forecasting math on those 438 allowed failures? Because, as it turns out, not all forecasting is created equal. We essentially have two very different methods here. There are short-term projections, which ignore past failures to focus entirely on recent spikes, versus context-aware calculations, which factor in your entire 30-day sliding history of system health. Short-term alerts, sometimes called ahistorical alerts, are fantastic for catching sudden, massive spikes in errors. But they have a blind spot. They assume you started the day with a completely full error budget. The danger here is that ahistorical alerts might completely miss a slow, cumulative degradation. Think about it. If your system is quietly bleeding out 2% of its budget every single day, it might never spike high enough to trip a short-term threshold. But over a month, you will still completely violate your SLO. And that is exactly where context-aware alerts become absolutely vital. To really map out the mechanics of the context-aware approach, we have to shorten the historical lookback to 26 days. Why? To accurately accommodate a 4-day forward projection window. Let's say you want to know if you're going to run out of budget in the next 4 days. Well, you can't just take a full 30-day history and slap 4 future days on top of it. Mathematically, you'd be evaluating a 34-day window against a 30-day budget constraint, which just breaks the model. Instead, you take the actual, real-world data from 26 days ago up to yesterday and combine it with a mathematical projection of the next 4 days, based entirely on today's current baseline failure rate. The actual procedure involves these 6 precise steps. It seamlessly combines your past 26 days of reality with 4 days of extrapolated performance. Step 1, you start by pulling the actual totals of your past 26 days. Then, you store those totals. Step 3, you find your current failure rate over the most recent 1-day window. Step 4, you multiply that current 1-day rate to confidently project out the next 4 days. Step 5, you add those projected 4 days back to your historical 26 days to get an adjusted 30-day window. Finally, step 6, if that newly synthesized 30-day total exceeds your 438 allowed failures, the system triggers the alert. It is a brilliant, highly dynamic way to ensure your alerts are actually sensitive to the real historical context of your system's health. It tells you if today's spike is going to be the final straw for a budget that was already depleted weeks ago. Okay, Section 4, Time Series versus Event Data. Just as we get the forecasting math totally figured out, we hit a massive plot twist. And this twist depends entirely on the type of telemetry data your system collects. This is where things get incredibly compelling. If you are running a highly stringent 4 nines SLO, that's 99.99%, every single second matters. Why? Because your total monthly downtime allowance is less than 4.5 minutes, just 4.38 minutes for the entire month. That is practically zero margin for error. If you are using traditional time series metrics, where data is forcefully aggregated into 1-minute buckets before it is ever evaluated, you are severely handicapping your ability to measure reliability. Here's the kicker. If you use traditional 1-minute time series aggregates, and your success rate drops to, say, 94% for just a moment, the entire minute is declared bad, which means you just burned 25% of your entire monthly budget in 60 seconds. No way, right? But it's true. Because time series data only gives you a binary good minute or bad minute, it completely lacks nuance. Even though 94% of your requests in that specific minute were perfectly fine and users were succeeding, the aggregate metric rigidly fails the whole minute. One single minute of slight degradation just wiped out a quarter of your entire monthly allowance. It's just a mathematically brutal way to manage a highly available service. When you look at the two architectures side by side, it's pretty clear. Time series data destroys stringent error budgets through coarse aggregation. Structured event data, on the other hand, gives you the exact request-level granularity needed to safely and accurately measure failure. With event data, if 94% of requests succeed, you only subtract the 6% that actually failed from your budget. The healthy traffic is properly preserved. Plus, when an alert fires, time series data only tells you that the system failed at a specific timestamp. Event data actually contains the rich, structured context to tell you exactly who was impacted, what failed, and why it failed. Which leads us to our final section, Section 5, Acting on Burn Alerts. Because knowing you're going to breach your SLO is really only half the battle, right? The other half is fixing it. Your very first action when an alert fires is to evaluate the trend. A sudden cliff drop in your budget requires a vastly different mitigation strategy than a slow, persistent bleed. A sudden drop might mean a bad deployment or maybe a severed network dependency, something you can often roll back or reroute quickly to stop the bleeding. A slow bleed, though, that is much harder to detect without the context-aware alerting we talked about earlier. It might be a subtle memory leak or an architectural bottleneck that only shows up under specific load patterns. But identifying the shape of the burn instantly informs your triage strategy. By coupling high cardinality event data to your SLOs, engineers can instantly debug these exact points. You move from a panicked, chaotic alert to an immediate, targeted investigation of the root cause. This is the profound relief that modern observability offers. You aren't just staring at a dashboard showing a random CPU spike, frantically guessing what went wrong while your budget goes up in flames. Instead, you can dive right into the raw events and see that, for example, only users on iOS devices who are trying to access the checkout service with a specific holiday promo code are failing. You know exactly who is hurting and exactly why. That level of high cardinality precision turns a potentially hours-long, all-hands-on-deck incident into a rapidly solvable, highly isolated bug hunt. So, here is a provocative thought I want to leave you with regarding your own team's alerting strategy. If your current threshold alerts only tell you the system is broken after the users have already suffered, isn't it time to start proactively forecasting your failures instead? Implementing SLO-based error budget alerts, powered by rich event data, fundamentally transforms how you respond to system degradation. It takes you out of reactive firefighting and puts you into proactive, targeted engineering mode. Start forecasting, start utilizing structured events, and really take control of your reliability. Thanks so much for joining me for this explainer, and I'll catch you next time.